Alright guys, we are back reviewing vector applications. I have two examples I'm going to work out with you today, and this first one is going to focus on, and I actually already have it kind of listed in there, on resultant forces, and the second one is going to be on the navigation, which is where you're using your bearings or headings or whatever you want to call that. So these are the two types, and hopefully this will review most of the concepts that you need to know or need to get some help on. So here we go. This first one is dealing with, and it gives you some, these two problems have some pictures to help you out, but we have forces with magnitudes of 35 pounds, which is listed for you, and 50 pounds act on a hook, which is kind of shown in that figure down below. The angle between the forces is 30 degrees, which again is in the picture below. We need to find two things here. We need to find the direction. And again, remember direction. If they say direction, you're looking for theta in standard position. So that's going to be theta starting at the positive x-axis going in a counterclockwise direction. So I'm looking for theta. And I want to find the magnitude of that resultant vector. So if we call that resultant vector r, I'm going to be finding the magnitude of it. So again, I have to find the resultant vector. Now before you get to a resultant vector, you need to have the two vectors that we need to combine to get that resultant vector. So that's where these two vectors right here come in. We need to find the these two vectors so we can add them up. So I'm going to start with the easy one, the 50-pound vector. I'm going to label it here as vector v. Just want to give it a name, so I figure v is a good enough name. And that vector is going to be going to the right, which means you just need to label that vector in its component form as 50, 0. Again, if you're going left, right, up, or down, we don't need to find these vectors in trig form because we really don't have any crazy angles to deal with. 50, 0 is perfectly fine. Remember, 50 is the length, which represents the magnitude or the force of that vector. So I know it has a length of 50, which is easy to calculate when it's just going to the right. The second vector I'm going to call vector w, just because I want to give it a name. And this one, because we have an angle here, I'm going to start by just putting this in trig form. So trig form, as a quick review, is going to be magnitude of the vector, so magnitude w, cosine theta, and then magnitude w sine theta. Anytime you have an angle that is not 0, 90, 180, or 270 degrees, then you can just plug in the vector in trig form, and all you got to do is evaluate any trig functions if you're able to do that. If you can't, you got to use your calculator, but same difference. So we happen to have the magnitude of this vector. The magnitude is 35 pounds. And we have the direction. We have theta, which is 30 degrees. So I'm going to go ahead, I'm going to zoom in here, but I'm going to take those two numbers and plug them in to vector w. So this is going to equal 35 cosine 30 degrees and 35 sine 30 degrees. So, oops, there we go. In this case, I do want to simplify that because I can. Because we know that the cosine, hopefully you know, the cosine of 30 degrees is going to be radical 3 over 2. So that's 35 radical 3 over 2. And sine of 30 degrees is going to be 1/2. So that's just 35 divided by 2. And again, I'm leaving it in this form for now. I mean, if we will here in a minute, go ahead and put this in decimal form, but right now we can just leave it there. Okay. So that's our first step. We have to find the two vectors. And again, remember our goal here is to find the magnitude of that resultant vector and the direction of the resultant vector. Now, they give you a visual, and this is always nice to kind of have, even though it's not really required, but for this problem at least. When we add these two vectors together, we are going to get a parallelogram. So this resultant vector is going to serve as the diagonal of that parallelogram. And as I said, it's not exactly required for this, but it's kind of nice to know. If I kind of drew these final two sides. I kind of guesstimated it as best I could here, but that should form a parallelogram, which is nice when you have maybe a horizontal and a vertical vector being added together. You know that parallelogram would be a rectangle. But anyway, that's what it's going to look like without these two pieces in there. I need to find the magnitude and the direction of this vector r right here. Okay, so here we go. The way to do that, to find vector r, we are going to add vector v and vector w, which means I'm going to take that 50, 0, and I'm going to add it to this crazy guy, 35 radical 3 over 2 and 35 over 2. Now, you can put this in terms of I and j. Make sure you're aware, maybe on the next one I'll do that. Well, other examples, I could do that, but here, it doesn't matter, as long as you know how to add these up. So for the first one, this is where you may want to start getting your calculator out. Just make sure when you use your calculator, we try to store these numbers as best we can, which shouldn't be an issue here. So I'm going to start with that 35 radical 3. I'm going to divide that by 2, which is about 30.31 plus 50, which is 80.31. So I'm going to get 80.31. I'm going to go ahead and store that, or just make sure you type in a bunch of decimal points so you don't screw up your answer. And my other answer is, half of 35, so 17.5. Okay, so that is vector r. So we are good to go. Now, all I need to do now is find the magnitude and the direction. So, just so you know, the magnitude, we have a formula for that. We're probably good to go. In order to get the direction, I'll just kind of draw this vector on its own little plane over here. So here's vector r, and when I find the direction, it's really nice to kind of just set up a right triangle, which is what I'm going to do here. So I'm going to draw a little right triangle using my vector. Now, vector r, again, is 80.31 and 17.5. So this is going to be 80.31, and this is going to be 17.5, and I want to find the direction. So I want to find theta. So to find theta, I'm going to go, in this case, I have opposite and adjacent sides, so I'm going to go tangent inverse of 17.5 divided by 80.31. And again, I have that 80.31 saved on my calculator, so I'm going to use the actual number. So I'm going to go tangent inverse 17.5 divided by 80.31, and we are going to get, if we're in the right mode, I'm in degree rating mode, but I'll fix that. You're going to get about 12.29 degrees. So there's your direction, and the magnitude of the vector is going to be equal to the square root of a squared plus b squared. So 80.31 squared plus 17.5 squared. And again, think of this like a right triangle. Well, it is a right triangle, so you don't have to, but the hypotenuse is really what we're looking for, and that's Pythagorean theorem, which is really where this formula comes from. So when you plug that in, so you go second square root, and I'm going to plug in that 80.31 squared plus 17.5 squared, you get about 82.195, so I'm going to say about 82.2 pounds. And that's how much force is acting on that hook. So that is your magnitude, and then obviously up here is your direction. So that's, a lot of the times when you're doing resultant forces, those are the things we're looking for, so that's a pretty common problem right there. So that is, again, resultant forces. Now the next one I have here is just dealing with headings, which is your bearings and things like that. So this one we have a picture as well to go with this. We got an airplane's velocity with respect to the air is 580 miles per hour. They just gave me a magnitude there, and they're telling me it's headed in the direction north 58 degrees west, which you can kind of see that angle written right there. And then next up they say the wind at the altitude of the plane is from the southwest and has a velocity of 60 miles per hour, and they're giving you that figure as well. Notice here they're even drawing the parallelogram that gets formed here. So when you kind of, that's really bad. But if you see this vector right here, that's your resultant vector forming that diagonal, that parallelogram. So you can kind of see that's kind of neat. All right, so they want the true direction of the plane, and what is the speed with respect to the ground. So what that means is they're wanting to find this resultant vector, and they want to know what direction is it really heading in, because that wind's going to kind of blow it off course just a little bit. And then the speed is the magnitude of that vector, because they say with respect to the ground. So as you're looking at it from the ground, how fast is it actually traveling? And that's with the wind kind of pushing on a little bit. So here we go. We got to find, just like before, we have to find these two vectors. I'm going to call this vector v, and I'll call this vector w. Actually, I'm going to call the first one, it's a plane, so let's call it vector p for plane. So we have that. Okay, so starting off with vector p, and this is where you have to pay attention to your headings, because the heading I have here is 58 degrees. So that's not theta. Remember, theta starts at the positive x-axis and it goes here. So right now we have that 58 degrees. That starts at the northern axis, so that means I'm going to add my 90 degrees to 58 to get theta. Not times, I did times in my calculator, sorry. So that's going to be 148 degrees. I don't know why I use a calculator for that, but whatever. So when I write this up, two things that I know the magnitude, which they gave me right here in the problem, is 580 miles per hour. And again, they gave me the heading, but they gave it to me as like a bearing. So I had to find theta myself. So theta, again, is 148 degrees. So this vector is going to be 580 cosine of 148 degrees. And 580 sine of 148 degrees. And then vector w, and again, I can write that out as decimals, and I'll do that as I'm doing my calculations later, because that one's kind of ugly. But I can do vector w right now. So vector w, I'm looking down here at this guy, and they're giving me the angle for vector w. Notice that is theta, and the reason why I know it's theta is because it is starting at the positive x-axis and going counterclockwise. So I have theta, and the wind is 60 miles an hour, so I have my magnitude. So this is going to be 60 cosine 45 degrees and 60 sine of 45 degrees. And because these are values on our unit circle, we can simplify that. I know my right triangles. So this is going to be 60 times radical 2 over 2 is 30 radical 2, and then 30 radical 2 again. So that's me plugging in radical 2 over 2 for cosine and for sine and just simplifying it. So I have my two vectors, and just like before, we're going to add those vectors up. And as I said last time, I'm going to do this in terms of I and j this time, just so you can kind of see it both ways. So if I wrote these out in terms of I and j, this would just be when I add up my resultant vector here. I'm going to go vector p plus vector w, and vector p is going to be 580 cosine 148 I, and then plus 580 sine 148j, so that's vector p, and I'm adding that to vector w. So I'm going to take this vector and I'm going to add it to the second vector, which is 30 radical 2i plus 30 radical 2j. And again, that's the same thing as me just adding these vectors in component form. I'm just going to go ahead and use my calculator at this point to figure out what the heck that is. So my first term, I'm going to go 580 times the cosine of 148 plus 30 radical 2. So this is going to give me negative, so for vector r, I'll put it back in component form here. I'm going to go negative 449.4. And I'm going to store that as a on my calculator because it's my horizontal component. And then I'm going to take my 580 sine 148 plus 30 radical 2. and I'm going to get 349.78. And I'm going to store that as B on my calculator. Okay, so now I have vector r. So at this point, just like we did before, they want the true direction and the speed. So I'm going to take this vector, I'm going to graph it, and again, it doesn't have to be to scale, it doesn't really matter, but here's vector r. It doesn't need to be in the right quadrant, it's kind of nice. But I'm going to set my triangle up here, and this is going to be negative 449.4, and this is 349.78. So define the direction. First thing, well actually let's find the magnitude because that's pretty easy to do. So the magnitude of vector r is going to be the square root of a squared plus b squared. Now on my calculator, I said I was storing these numbers on my calculator. If you don't know how to do that, if you have the TI calculators, the number right above your on key is your store key. So when you type in a number, you can hit store and then hit alpha A and it'll store it. And I did that. So on my calculator, I'm just going to type in literally the equation. The magnitude is the square root of a squared plus b squared. So the square root of that negative 449 squared plus 349 squared. So when I do that on my calculator, I'm going to get the square root of a squared plus b squared. I'm getting 569.5. And again, this represents speed, so miles per hour, I believe is what it was. And there we go with our magnitude. So we have that piece. Now I want to find the direction. Now in order to get the direction, remember this right here is your theta, and I'm going to do direction in terms of theta, and I'm also going to do it in terms of a bearing or a heading, just so you can kind of see both. But regardless, I need theta first, so that's my first step. So in order to do that, I'm going to first find this angle, and this angle I'm going to use the Greek letter alpha. I'm going to find alpha, and when I do that, I am just going to do my trig ratios again. Remember, I called that B and I called that A. So I'm going to do, again, tangent. I'm going to go tangent inverse, and I'm doing B over A. In other words, 349.78 divided by negative 449.4. So I'm going to go second tangent of B divided by A, and I get about 37.3 or 37.9 degrees. So the way this is going to kind of solve this, and I got to remind you, I am in the second quadrant, so I don't really actually need that negative. I just remembered that. So if you type this in without the negative, then you'll see it just gives you that positive answer. So I'll go ahead and switch that on mine. Well, you can't see it anyway. I guess there's really no point. But understand that angle is just 37.9 degrees. And again, the direction or that angle, the sign here, that doesn't really matter. Just treat it like a regular triangle, because you just really need to find that angle in that triangle. So you can just think about those two links as just positive links. But this is going to be about 37.89 degrees. Now, once you have that angle, if I want theta, I'm just going to go 180 minus that answer. So that's how I can find theta. So if I want to do that, not a big deal. I'm going to go 180 minus that number, and I'm going to get 142.1 degrees. So that's theta. If I wanted a heading or a bearing, well, I know that this little piece right here is 90 degrees, so I just need to find out what this little piece is, because I'm going to go, my bearing is going to be north however many degrees west. So I'm just going to go 90 minus that 37.89. So that's going to be, that means this piece right here is 52.1 degrees. So that's going to be my 52.1 degrees west. And that's how you would find your heading, bearing, heading, whatever you want to call it. All right, so that is resultant vectors dealing with headings and bearings, and well, without dealing with headings and bearings. So hopefully that helped you out, and you have a better understanding, and good luck moving forward.